Okay, so in the last lecture, we solved this problem for membrane reactors. So this elementary reaction, it's a gas phase reaction, by the way. A goes back and forth to H2 plus C, so this is a reversible gas phase reaction. We said it's carried out isothermally and isobarically in a membrane reactor, and here's some information about the reactor. And we solved that in Python for the membrane reactor, and then we compared it to the case where we had a PFR. So the difference between the membrane reactor and the PFR, in the membrane reactor, hydrogen diffuses out of the membrane with a pretty significant mass transfer coefficient, and this pushes the equilibrium to the right, allows more product to form. So we solved that. We solved the membrane reactor using mole balances in terms of dF/dV, and that's because we said one of the key points out of the membrane reactor lecture was that we cannot any longer use conversion to solve for the membrane reactor. So we used dF/dV, we used the balance in terms of F terms. And then when we did the PFR solution, we basically took the same model and we just eliminated the diffusion rate from that. So we also solved that PFR mole balance in terms of F. So we used interdependent mole balances that look like dF/dV. So we used the mole balances in F terms and not X terms. And that's perfectly fine to do it that way. However, for the PFR, we can indeed solve in terms of conversion. There's just one reaction being carried out. So that would have been perfectly fine. And so to demonstrate this, that's what I want to do here. Let's solve the PFR balance, but let's go back to using F terms just to demonstrate that it should be identically the same thing. So the PFR, to solve a PFR in terms of X, first step that I'm going to do is I'm going to write down my mole balance. So that's going to be dXA dV is equal to minus RA divided by FA naught. And the next step would be then to write down the rate law. So minus RA is equal to KAF CA. And in fact, let's just say KAF times CA minus CC/CH2 divided by the equilibrium constant Kc. So now we have over here our rate law is in terms of concentration, and we need to put it in terms of X. So we're going to use the concentration equations. So Ca is equal to Ca naught 1 minus Xa divided by, and this is going to be 1 plus epsilon x. Epsilon is equal to Ya naught delta, and in this reaction, delta is going to be equal to a positive 1. So I have 1 mole on the reactant side and 2 moles on the product side, so delta is going to be equal to 1. Ya naught is also equal to 1 because pure A is fed, so then Ca is going to be equal to Ca naught 1 minus Xa divided by 1 plus Xa. So now I can do the same thing for CH2 and Cc. So CH2 is going to be equal to Ca naught Xa. So no H2 is fed over 1 plus Xa, and this is going to be also equal to Cc. So no C is fed, no H2 is fed, and since the reaction stoichiometry is the same for them, they're going to have the same expression. So now I could substitute all of these equations for concentration back into my mole balance. So let's do that. So I have minus Ra is equal to KAF Ca. So Ca naught 1 minus X divided by 1 plus X minus Cc times CH2. So this is going to be Ca naught squared, Xa squared divided by 1 plus Xa squared times Kc. And so if I wanted to solve this, I would basically separate the variables and solve. So let's do that. So I'm going to have, this is going to start to get messy here, but I would have dxa divided by this large term in brackets. This should be, well, these should be a's to be consistent. And this is going to be equal to the KAF divided by FA naught, and then times volume. And we know that the volume is equal to 500. So I'm going to actually use the Wolfram alpha integral calculator to calculate this. So I'm going to go to, this is actually integrals.com. This allows me to enter in a integral, which I can integrate. So I'm going to say integrate, and then I have to make an equation. I'm going to say my equation is equal to Ca naught times 1 minus x divided by 1 plus x. In this case, Ca naught is equal to 0.2. So we'll say 0.2 times 1 minus x divided by 1 plus x. We'll say minus, and if I go back here, Ca naught squared times Xa squared divided by 1 plus Xa squared times Kc, where Kc is equal to 0.05. So we'll say minus 0.2 squared. Let's just be careful there, 0.2 squared times x squared divided by 1 minus x, or actually it's 1 plus x squared, and let's say, and just times 0.05. That should be that, and then one more, and then we'll say to the negative 1. Push enter, and let's see that if I wrote my equation in correctly, which it appears that I did. So I now get a value for this. So this equation right here. And if I go back to my equation, what I want this integral to actually be equal to is this quantity here. If I multiply this out, then I get that this is equal to 35 liters per mole. So the liters per mole makes sense. That's what also the units over here are going to be. I have inverse concentration in both of these terms. So I have a squared over here, but then this is in units of concentration. So I have inverse concentration. So let's go back here, and so I have basically two options. One, I could use an algebraic solver for x in order to find a value of this expression that equals this 35. Alternatively, I can say just start guessing values, so I know my initial conversion is equal to 0. So let's, guess from 0 to 0.5 and see where we get there. So going from 0 to 0.5, it says my standard computation time is exceeded. So that's, if we recall, the equilibrium conversion that we got in the last example was around 0.45. So that basically says we can't get past 0.45. So what if we didn't know that? Okay, the standard computation time is exceeded. So I'm going to say now from 0 to 0.25. Okay, so I get a value 1.8189, so that's not large enough, so why don't I increase that? So let's say 3.5. So now I'm getting a larger value, still not large enough. And I'm basically going to creep up here since I know what the answer is. Now I'm getting somewhere. So what about 446? And basically, if I would have taken the value that I obtained from Python, I should be able to get the answer, and here I get 35. So that tells me that if I integrate this quantity, so I need to integrate between xa equals 0 and xa equals 0.44, let's go over here, 447213, 447213. If I do that, then I get 35 on this side and 35 on this side. So this is my equilibrium conversion right there. So xe equals 0.447213. This is the max conversion that I get possible, and also the conversion at the reactor exit. So when V is equal to 500. So I solved this side of the integral using Wolfram alpha. Alternatively, we could have gotten a solution for this. So Wolfram alpha does give us a formula here. I could have typed this formula into Excel and used the goal-seek function to find x. Maybe some of you have fancy calculators that will do that for you. Any way that you do that is fine. So that's the same PFR example, solving in terms of, or using x terms to solve the mole balance instead of f terms. I just wanted to demonstrate that you're getting it's the exact same answer through a different solution procedure. So the other way that we can do this is just to use the equilibrium conversion. So I don't even, in this case, need to solve mole balances. Equilibrium conversion is based on thermodynamics and hence kinetics, not even part of the picture. So if I go back to this reaction, the reaction A goes back and forth to H2 plus C, I can set up an equation for my equilibrium constant. So I know that Kc, the equilibrium constant, is equal to Cc CH2 divided by Ca. And I know what this is equal to. This is equal to 0.05 molar. And actually, it's 0.05 molar. And I also have expressions for these quantities already. They're the same as they are right here, Ca, CH2, and Cc. So I could enter all of that into here and solve for what value makes that equal 0.05. So I could enter all of that into this equation and basically solve for the value of x that gives a value of 0.05. So let's do that. So the Cc and CCH2, so basically I'm going to have 0.05 is equal to Ca naught squared xe squared, where E is the equilibrium conversion, and this is 1 plus xe squared down here on the bottom. And this is going to be divided by Ca, so Ca is going to be equal to Ca naught 1 minus x times 1 plus xe. So if I simplify this equation, I get Ca naught xe squared divided by 1 plus xe, 1 minus xe. And this one I really am going to use the goal-seek function to solve. So I'm going to pull up a Microsoft Excel worksheet. I'm going to define some variables. CA naught is equal to 0.2, KC is equal to 0.05. And then I'm going to give a guess for my conversion, and as we already know what that is, so I'm going to give a guess that's kind of close to it. And now I'm going to type in my equation here for my equilibrium constant, so CA naught times XE squared. So we'll say divided by 1 plus XE times 1 minus XE. And let me make sure that I got that correct. I think that I did. So now I'm going to use the goal-seek function. So to do that, I'm going to highlight this cell. I'm going to go Tools, Goal-seek. I want this to be equal to 0.05. And the cell I want to change is this one. So I push OK. And I get a value of 0.44. So I'm not getting an exact answer because this isn't exactly 0.05. I could play with this answer, and in fact, if I go back to Wolfram Alpha, and I calculate this value that I got here, and I put it in my Excel worksheet, I get a lot closer to this 0.05. So, moral of the story, I can solve this problem for this PFR at least 3 different ways. Here I got the same thing, equals 0.44, and I don't remember what it was, so let's go back and check. 7213. So I solved this PFR problem 3 different ways. In one way, I wrote an interdependent set of ordinary differential equations for the flow rates of my different species, and I solved it that way. Another way that we did here is I wrote a mole balance in terms of conversion, because in the PFR case I can do that. I just have one reaction and I have no diffusion out of the reactor, so I can write a mole balance in terms of conversion like we've done several times now in this class, and I solved that, and I get that at the reactor outlet, since we have hit equilibrium well before that happens, I get the equilibrium conversion. And then the other way, as I said, since we know that we're hitting the equilibrium conversion well before the reactor exit, let's take kinetics out of the picture entirely and just solve an equilibrium calculation. So we did that and we get the exact same answer. So 3 different ways to solve this PFR problem.